Hey, it's Nathan, and I've wanted to talk about what I do research-wise for a while now, and I haven't really known how to do that. So, in order to start doing that, I need to start telling you about the basic things that come up in what I do. And the first thing, which is the springboard off of which everything else can be talked about, is that of what is a discrete topological dynamical system. So, to start, a discrete topological dynamical system is a continuous self-map of a compact metrizable space. And that's why we call it topological, is because the space is just metrizable. I don't have a fixed metric or a fixed metric geometry that I care about on the space. All I care about is that you can put one there. And the qualities of the map, the continuity of the map, is actually just a topological condition. I don't need a metric to describe continuity. However, when you do enforce any particular metric that you choose, you can then reorient your continuity definition to be in terms of that metric, which is what you would see in a calculus class. When we're studying these systems where we may not have a fixed metric, the thing that we usually think about is, how do we describe long-term behavior of the system? What happens after very, very many time steps? Or what happens after a long time? And so I need to tell you what a long time is, or what a time step is. And really, it's just an iteration of this continuous self-map of that compact metrizable space. So what we will often look at is we'll look at how do iterates act. So we'll often write in this field of math the map to the nth power. And that doesn't mean taking the output and raising it to the nth power. What that means here is it means the n-fold composition of the map with itself, which is still a continuous self-map of the compact metrizable space to itself. So each of these compositions is also a discrete topological dynamical system in its own right. There are a lot of different examples of these things when we're studying discrete topological dynamical systems. The two easiest ones to talk about right out the gate with no background are what are called circle maps and also directed graphs. Probably the most used example for illustrating a simple example of a topological dynamical system is that of the doubling map, which is a map from the circle, which we'll think of as the interval 0, 1, but then you identify the endpoints. So you have a line and you just glue 0 and 1 together. So I'll write that as the interval from 0, 1 or mod, or divided by the equality 0 is equal to 1. And so you can still write it on a coordinate grid. You just have to remember that whenever you hit 1, you're actually at 0 and vice versa. In the doubling map, what it does is it just takes in an x value and outputs twice that x value mod 1. So what that means is that you go ahead and take whatever number in the unit interval that you have, you multiply it by 2, and you just kill the whole number part of that result. So you get something that looks like this. The other example of discrete topological dynamical systems that come up all over the place is that of directed graphs. There's a lot of different ways to formulate how you would define a dynamical system based on a directed graph, but the simplest way is to take the directed graph itself as a topological dynamical system. There are requirements, though. So in this example that I've drawn, this is just a period 4 orbit dynamical system, which means that all of the points have period 4. It's a single orbit, which means that you can generate the entire space by just picking a point and iterating the map over and over again. Here, it only takes 4 times to do that. And you can define the map based on the arrows. So the thing to remember is that the T-map is a continuous function of the space to itself. So here, our space would be x is equal to a, b, c, d for the different vertices in play. And then T of A is equal to B, T of B is equal to C, T of C is equal to D, and T of D is equal to A. And the thing to note here is that because t is a function, there can only be a maximum of one outgoing arrow from each vertex. We often call this value the out degree of a vertex, which is usually written as degree sub plus sign of the vertex. And it's equal to the size of the set of edges that come out of that vertex. So here, in order for a directed graph to be a discrete topological dynamical system, we require that the out degree of every vertex in the graph is exactly 1. So now that we know what a topological dynamical system is, we can start talking about some different basic computations that you may want to start doing on these systems to sort of get an idea of how they look as mathematical objects. This board is just going to be like a list of definitions, really. So first, probably the most obvious thing that you might want to look at is the forward orbit of a point, which is just where does the point x go? It's all of the forward iterates, or the t to the n of x's that you can make, where n is greater than or equal to 0. Alternatively, and this is a little bit, I guess, counterintuitive if you're first starting to think about dynamics, because you're like, oh, I want to think about long-term behavior. Why would I go backward? But oftentimes in dynamics, thinking about pre-images instead of forward iterates is more helpful because it gets you more information about how the system is moving things around in total. So the backward orbit is also defined, and it's looks a little bit different because you have to remember that pre-images of points are sets. They're not points, unless the function is a bijection, and then your dynamics are boring. But anyway, that aside, you have to remember that pre-images of points are sets and not points themselves. So when we define the backward orbit, what we do is we take a union over all n of the n-fold pre-images of a point. And so this answers the question of, okay, where could a particular point have come from? You can also go ahead and just make these two ideas their own mathematical object by unioning them together. We call that the full or the grand orbit of a point when you take those two things together. And then there's other like special types of orbits that can occur within your dynamical system. And these are the periodic ones. So if you think about your sine or cosine graph, that's where your intuition should come from. Your point should return to its place after a period of time. But here, instead of with like a trig function, our time is discrete instead of continuous. So when we were talking about a point returning to where it started, that means that after a finite number of iterates, it comes back. So we say a point x is periodic if t to the n of x is equal to x for some n, a natural number. The smallest n for which x returns to itself under iteration of t, or in other words, the smallest period of x, is defined to be what is called its prime period. And if x doesn't have an n for which it returns to itself, we would say that the prime period of x is infinite. We can also collect together all of the periodic points of a particular period n into one set. We often will denote this as per sub n of t, or per n of t. And so this is just all of the points that have n as a period. It may not be the case that n is the prime period of a point within per n of t. Further, you can have points that eventually become periodic ones. What I'm talking about here is called pre-periodic. And so what a pre-periodic point is that it's a point such that after k iterations, it enters into a periodic set. And then the last type of point that is important in terms of these periods is that of fixed points. And so your fixed points, or your fixed set of t, is just all of the points that have prime period 1. That is, they return to themselves after one iteration, or they just stay put. So if you look at this example of a discrete topological dynamical system, which is just a directed graph in this case, we can easily see that periodic implies pre-periodic, but the reverse is not true. So we'll note that A and B are pre-periodic points. From this graph, we can see that the forward orbit of A is the set A, C, D, and E. The backward orbit of E is dCABE, and then the fixed set of T is just the point F, because that's the only point that returns to itself after one iteration. So if we go ahead and go back and talk about the doubling map, we can go ahead and see that there are also like visual ways to calculate these things when you're not using a graph. So I guess that was kind of a weird sentence to say, because in both cases they're graphs. It's just that one is a directed graph and the other one is like a graph of a function. So what I mean by that is that there are more, I guess, geometrically involved ways to think about these things instead of just doing things on a directed graph. Because in the case of the doubling map, you don't have a directed graph, or the directed graph would be infinite. It would be really gross to write down. So what happens with the doubling map is that because you can graph it as a self map of the unit interval to itself, and then you just identify 0 and 1 in your brain, we can really easily figure out what the fixed set of this map is. And the way that we do that with circle maps is that we draw the graph on the unit interval as a function of the unit interval to itself, and then we draw the line y is equal to x. If the map ever hits the line y is equal to x, then we know that wherever those intersections are is a fixed point of the map, because the input would then go to itself. So here, if we look at the intersections of the doubling map with the line y is equal to x, we just get 0. And the reason we just get 0 is because 0 and 1 are the same thing in this context. And then there's also an interesting thing that occurs when you go ahead and you do the backward orbit of a point. So to illustrate this, I'm just going to start with 0. So if you go ahead and do the backward orbit of 0, you need to find all of the points that end up mapping to 0. So here, that would be 0, and then the other point that does this is where we have the dotted line from y equals 1 to y equals 0, which is at 1/2. So under the first preimage of the doubling map, the thing that is strictly in just the first preimage is 1/2. And then when you do the preimage again, what we need to figure out is to get new stuff. We already know where 0 came from, right? It came from 0 or 1/2. In order to figure out the next preimage, we just need to figure out where 1/2 could have come from. So what we do is we go on the y-axis, we draw a horizontal line to figure out what would have hit 1/2, and we find that the 2 points that would have hit 1/2 were 1/4 and 3/4. And so the terms that are in strictly the second preimage of 0 are 1/4 and 3/4. And then if we do that again, right, we already know where 0 came from, we already know where 1/2 came from, we need to figure out where 1/4 and 3/4 came from. Well, 1/4 came from 1/8 and 5/8, and 3/4 came from 3/8 and 7/8. And you sort of hopefully see the pattern here, is that after every preimage, you double the number of things that in total are strictly a part of that preimage. And that's one of the reasons that this gets its name as the doubling map. In particular, if you continue this preimage process of 0 forever, what you end up getting is you get all dyadic rationals will eventually map to 0. So dyadic rationals, if you are not familiar, are those numbers that are of the form m over 2 to the nth power, where m is less than 2 to the n, and m and n are natural numbers. I've given you some examples of these systems. I've told you some computations that you can do with them. And when you're doing proof-based mathematics, or you're doing theoretical math, or you're doing just, I guess, math in general, right? One of the things that we want to know in math is we want to know, how do you tell objects apart? What is the right way to think about these things as encoding a particular bit of info and our other objects encoding that same bit of information? And so for topological dynamical systems, the thing that distinguishes them is called a topological conjugacy. A topological conjugacy works as follows. Say you have two topological dynamical systems. One is xt and the other one is ys. So x and y are your compact metrizable spaces, and t and s are your continuous self-maps of those compact metrizable spaces. In a conjugacy or a topological conjugacy for these topological dynamical systems, what you have is you have this categorical diagram. So I guess it's not really categorical because they're not categories running around, but it has the same flavor as a category theoretic thing would, or an algebra type thing would when you're doing algebraic topology. But you have your X maps to X via T, and you have Y maps to Y via S, and then there's this map that connects them in a particular way, which we'll call H. And so H makes this diagram commute, which we denote by this swirly arrow inside. And so the property of H that makes it a topological conjugacy is that H is a homeomorphism such that H composed with T is equal to S composed with H. Another question that we usually have about mathematical objects is, well, okay, I now know how they're equal. Well, how do you tell them apart? And the idea here is that of invariance. So an invariant is any property that is conserved under the notion of equality. So here our notion of equality is a topological conjugacy. So an invariant will be any property that when you go ahead and move from your first dynamical system to your second one via your topological conjugacy, you'll still have the same value for that invariant, or you'll still have the same object for that invariant. One way we can express this is we can call it the collection of invariants. So if you go ahead and have the collection of invariants is equal to a particular set or collection, and that is not equal to the set or collection that corresponds to another set of invariants, then you know that the two topological dynamical systems are different. The way I phrase this is a little bit counterintuitive because there are many, many, many invariants of these systems. And really, in order to tell them apart, you only have to focus on one. And that's how you figure out if those collections are different. You just look at one particular invariant, calculate that invariant for one system and the other system, and if you see that they're not equal, then you know that the two systems are not, quote unquote, the same within this realm of thinking about topological dynamical systems. So I should tell you an example of one of these conjugacy invariants. And we've already looked at actually infinitely many of them. And those invariants are the number of periodic points of period n. And we can actually prove that the periodic points of period n is a conjugacy invariant rather quickly. So to prove this, we go ahead and let xt and ys be topological dynamical systems, and we let h from x to y be a conjugacy. Then you have this diagram which commutes. And so if we have a point that is a periodic point of period n in the topological dynamical system T, then the nth iterate of S applied to h of x is going to be equal to h of t to the n of x, which is just going to be equal to h of x, since t to the n of x is equal to x because it's a periodic point of period n for t, and then that implies that h of x is a periodic point of period n for s. Now, since H is a homeomorphism, H is a bijection, so if we go ahead and restrict the domain of that bijection, and it's a bijection onto the periodic points of period n of S, and so we have that the number of periodic points of period n of t is equal to the number of periodic points of period n of S. And so now with this proven, we can go ahead and tell apart different dynamical systems. Hopefully the difference between circle maps and a directed graph topological dynamical system is relatively clear from just looking at them and having a little bit of intuition of like, these feel like very different objects. But it might not be as clear that circle maps, that there are a lot of them in terms of this conjugacy idea. And one way we can see this is we can go ahead and look at the doubling map and then what I'll call the tripling map, which is the same thing as the doubling map, but instead of doing 2x mod 1, you go ahead and do 3x mod 1. In this case, we can go ahead and look at the fixed sets of each of these maps. And the fixed set of the tripling map is going to be 0, which again is equal to 1 in this particular context, because it's a circle, and 1/2. So those are the fixed points for the tripling map, 0 and 1/2. And then the fixed points for the doubling map, as we saw earlier, was just 0. So the sizes of the points of period 1 are different. And so the doubling map and the tripling map are distinct topological dynamical systems. In fact, for any n, the n-tuple map where you have n branches is distinct from any m-tuple map where you have m branches where n is not equal to m. So there are infinitely many circle maps to go out and study. Anyhow, so we went over what a discrete topological dynamical system was, or a discrete dynamical system, whatever you want to call it. So we went over what that was. I gave you some computations that you can do with those, gave you an idea of how to tell them apart, and then I gave you a proof of one of those things as one of the things that you can use to tell them apart, and then we looked at an example. So I think I've done what I've set out to do in this particular video. So that's it for this one. If you enjoy math stuff or learning more about math stuff beyond calculus, that's sort of the style of videos that I make here that are more on the academic side. I also do updates about how my PhD process is going or how my math academic life is going. So those are out there as well if you'd like to look at those. But anyway, as always, I'm Nathan. This one was Chalk. If you like these videos, you can subscribe for more, or you can just leave me a comment for things that you might want to see me talk about in the future. But anyway, that's it, and I will see you next time.